Okay, today we're going to start A2 chemistry, organic chemistry. Right, let's look at first the syllabus first. Right, I'll share screen here and let you look at syllabus. Okay, here we are. Here. So what are arenes first? Let me explain the arenes first. Now here arenes. Let's describe the chemistry of arenes exemplified by the following reactions of benzene and beta-benzene. There are two types of arenes they ask you here, benzene and beta-benzene. I'm going to show you what it means first. Okay, what are these two compounds? But here they say describe the chemistry, which means they want only the reactions. But in the question they ask you for the structure of benzene, which I'm going to show you now. Okay? So here we're going to come later. I'm going to screen sharing and go to a better place for us. Here, let's say if I were to write about what is benzene. Benzene is C. Oh yeah, I cannot write this. So let's see. Okay, let's try the other one. I can use the pen. Here, so the space will be big enough. Right? Here we are. If you talk about benzene, there are two things here. One is benzene, C6H6. Now it's called benzene. Okay? It has a structure like this. Okay. Now there are two ways to represent benzene. Like this. You've seen before in AS. Okay, and here. We'll explain this later. But this is called the delocalized model. The other one is the Kerkulé structure, which is they draw the carbon here and there to be accurate. Right? And these are all double bonds alternately. Alright? And here's your hydrogen here. Hydrogen here. So this is called benzene. This is called the Kerkulé structure. Kerkulé structure. Most of the time they prefer this diagram to this diagram, but this diagram is very useful for explaining reactions afterwards. Okay, you can see that here these are all hydrocarbons. Okay, what are hydrocarbons? In Form 5, the hydrocarbons contain carbon and hydrogen only, is it? Right? So you have learned in your AS, there's the first member or the first family is called alkanes. Alkanes, well, I'll go here. Alkanes have a general formula for CnH2n, 2n plus 2. Alkene, you also know alkene the general formula for CnH2n. For benzene, how do you recognize a benzene or an arene from an alkane? An alkane is very simple. See the ratio of carbon ratio to hydrogen is about 1:4 here. The alkene is what? 1:2. Right? So 1:4 to 2 is correct. Now here for benzene is because benzene is the first member, so C6H6. Okay. Now if I have a methyl benzene, here methyl benzene. Okay. What's methyl benzene means? I replace a hydrogen here with a CH3. For example, here I got CH3. Alright, and the hydrogen is kicked off, and of course here I have the ring. Okay, now to make it easier for you, I put the double bond here and the H here. So you can see that this is called methyl benzene. In your syllabus, they just mentioned these two compounds for starters, right? So remember now this one here will have how many carbons are together? 6 in the ring plus 1, so 7. So C7H. There are 5 hydrogens here, and plus 3 is 8. So the ratio of carbon is to hydrogen is about 1 is to 1 around there. Here also about 1 is to 1. Hydrogen is 1 is to 1. So when you see that short of 2 here, that means that you know that is, if it's 2 here, you know that it's alkenes. So it's less than 2 and 1 point something, it means it contains a ring here. Normally we will do only 1 ring. Sometimes you use 2 rings, but they will tell you. Okay. Now I'm going to today. I just want to show you. They ask you not only on the reactions of benzene, but the structure of benzene. Okay. I'm going to show you now the question. Question page 355. Okay. Now here's a question. You can see here. So now this is the benzene. C6H5, SA6, and borazine. Okay, now these two have something in common. They tell you here, because we don't learn this one. Okay, we don't learn the borazine, but it has something in common. So this is an application question. But look at benzene first. Okay, they say a benzene C6H6 and borazine B3N3H6 have planar cyclic structures. The question is, describe the structure and bonding in benzene C6H6. Okay, this is the first one. So they ask you for the structure. Now this is an application of your AS. I'll show you afterwards why. The second question here, which is page 54. Okay, briefly explain why benzene molecule is planar. Planar means flat. Remember now, you learn this AS, the shapes of molecules, right? And here, briefly explain why. So the two questions of why, it means you must give reasons. The mark is given for a reason. Here, 1 mark, 1 mark is 2 marks here. But the other one is 3 marks. Okay? Why the carbon bonds in the benzene are the same length. This is where we go into the whole idea. Okay, let's look at page 1 again. Page 1. Here. Here they are talking about the reactions right now. Of course, not only the reactions first, but of course the structure. Now here you can see my notes, can read up yourself. Methyl benzene, ethyl benzene, see that, okay? Ethyl means that C2H5 here. The ratio is approximately 1 to 2. See all the different types. Now the position of the other, they call this attached, okay, to the ring. One hydrogen here, of course, here would be 6 carbon here plus 2. Here should be what? Here should be C what? 8 H what? 4 hydrogen here. 1, 2, 3, 4. Okay, 1. See my 2, 3, and 4 here. Right, now here no more hydrogen. The hydrogen here has been replaced, right, by the CH3. So 4 plus 6 here is 10. See? So it's still less than 1 to 2, isn't it? So it still is considered to have a ring. So 6 carbons here, so there must be 1 ring here. Okay? So now the position, now all these 3 have the same molecular formula. Right? C8H10, all these 3. This one, this one. That's why they are all called methyl benzene, the dimethyl benzene. See, the name here, dimethyl benzene. All same. But to represent the position, so we take one of them as a reference point. Normally, the one up here, okay, as this reference point. This carbon is called carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. You can put carbon 1, 2, 3, 4, 5, 6, okay. But normally we to see the position of the methyl group here, we take the smallest number. naming is it smallest number here. Okay, so here we have got 1, 2 dimethyl. Dimethyl means 2 methyl benzene. And of course, here's 1, 3. Why? Carbon 1, carbon 2, and carbon 3. Okay, so here's carbon 1, carbon 2, carbon 3, and carbon 4. So it's 1, 4, 1, 4. Okay, so this is how they name it. Okay, now let's look at the some properties first. Okay, now remember all these. This benzene and your methyl benzene are found in your current petrol. That's why they are very toxic. Also, they are not solid in water. They are less because they float on top of water. There's a point on some physical properties. Physical means the melting point, boiling point, density. On here, all of physical properties. You can see here on melting point and boiling point. It's quite interesting to see, of course, melting point means a melting point here. You know what melting point? Melting point. The temperature when you change from what? Solid to what? To liquid. Okay. So this is the melting point. Boiling point is from liquid. Boiling point is from liquid to gas. Now, the interesting thing, of course, these all these things here, because they are covalent substance, right? Also, they are a bit well polar. They will have dipole attraction, so they are normally quite low in their boiling point. But of course, the more number of atoms, the more elements, the more number of electrons. That means they will have stronger van der Waals forces. That's why you can see there's across here. There's an increase, okay, increase in boiling point, right, to break the van der Waals forces. So here's van der Waals forces. Forces which of course increases with the total number of electrons there. Okay, so now these are a bit different as well, but because of the position and of course of the polarity. Don't worry about that. But now the important thing, of course, is the melting point. The melting point, you can see that. See, the melting point also talk about when the Waals forces, but how come this one is so low? Right? These two are higher, you know. 5.5 and 36 is higher. See, melting point talks about how you destroy the whole structure. You know that solid here. Solid here, when they form solid, they are arranged in nice in proper order. It means that the more stable the arrangement is, it means if it's a well-arranged molecule, remember all the molecules are stacked on top of each other. If they are well arranged, properly arranged, they will have a more stable, therefore they will melt at a higher temperature. So what causes the molecule to be well arranged easier? This is called symmetry. I'm going to write the word here, symmetry. 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 Sorry, M-M-T-R-Y. Or they call it symmetrical. Symmetrical. These two. See now, there's a line of symmetry here. It's a line of symmetry. Axis of symmetry. Okay, therefore these two can be arranged easier, more stable. Okay, so they are more stable. More stable. That's why they have higher melting point. Of course, this is higher because there's a more number of atoms, more number of electrons. Once when you destroy the symmetry, you put a CH3 here, right? So the symmetrical line is no more there. That means this is harder to pack each other. So lower the symmetry. This will lower the symmetry. Okay, lower the symmetry. Symmetry. That's why they they pack not very nicely, so they will have a lower melting point. Okay? So these are basic things, right? Now let's go on to the structure. Okay, now you can see here my notes can be all symmetrical molecules. Right? Now this is also, now you can also name this in another way, instead of 1, 2, 3, right? Opposite. Now this is the one. So this is called the this is the reference point. Okay. So opposite, directly opposite here is called the para, the P. Okay. It's called P position of para. Okay. On beside these two are the same, you can put here's 2 or 6, right? Here's 2 or 6. These two positions are called ortho. O-R-D-H-O. I forgot O-H-O-R or whatever, okay? That's ortho. Okay. Now, on here, these two parts are called the meta. M-E-T-A position, okay? Right? So sometimes you can refer to it as ortho. This is called ortho. Ortho dimethyl, this one is called ortho, right? Ortho dimethyl benzene instead of 1,2-dimethyl benzene. It's called meta-dimethyl benzene, right? It's called meta. It's called para-dimethyl benzene. This is called ethyl benzene. Okay, now, right? So that is on naming and some physical properties. Now, let's see how we can answer the question in the past year question. Okay, right? Now, this is the structure of benzene molecule. It's planar, flat. Okay, planar. Okay, this is planar. Or flat molecule. Okay, flat molecule. This is molecule. These are shapes. Right. Now, why? Now, all these are carbon. Here is carbon. Carbon. All these are carbon. So there are 6 carbon joined together. How did they come to this, this structure? Actually, at first, when they found benzene, benzene is found naturally in your, in your oil. They come from the ground. Okay, all those undistilled petroleum, right? The raw oil. So it's found there. Okay, so the benzene, when they first found and when they distill it, they found, well, this has a molecular formula of, I will put down here, C6H6. Now they can recognize an alkene, but what is this substances? What is this substance? So they could not think of it as the first. So this guy Hercules had a dream. He dreamt of 6 monkeys holding the tails together, which is the monkey is a carbon. So he come up with, it must be like this. Or 6 monkeys holding each other's tail. And the only way to suggest the formula is that there's a double bond here. Because carbon got 4 bonds, 4 is in. So here's 4, and 1 here, which is the hydrogen. And he was correct. But of course, he's wrong also in the sense that he accepted okay, why? Now this is your benzene. So now this is called, that's why it's called the Herculean structure. Now I'm going to see how this marry with the new structure called the resonance structure or the delocalized structure. Now, carbon, as you know, right? I'm going to draw it over here. Carbon is 612. Okay, it has got six electrons. Okay, so the electron configuration is 1s2, 2s2, and 2p2. Now this is in the ground state. So if you draw the boxes here for the orbitals, okay, here hydro, pair here, here, and here. But carbon, you done this before, right? Yes, right? As carbon bonds with substances, said to go to an excited state, C excited state, which is what? 1s2, 2s1, 2p3. So I'm going to draw these two here. So it's 1, 2, 3. Now the two electrons here are promoted to here. So now I got 2s1, 3p3, 2p3, sorry. So now in this case here, in your alkanes is sp3 hybridization. In your alkene is sp2, and here it goes sp2, 1s and 2p, right? So it forms an sp2. So now this is sp2 orbitals. I'm going to draw here. I'm going to use another color. Okay, wait. Okay, now I'm going to draw the sp2. Here, 1. Okay, there's a small little thing here. Don't care about it. 2, this should be bigger. Okay, 3. Okay, so and then this carbon same. sp2. See now, sp2 here. Same this carbon here. sp2, sp2, sp2. Same this carbon here. I'm going to draw a bit bigger so to show up. Okay, sp2, sp2, sp2. Same here. I just draw a bit bigger to overlap. Okay, sp2, sp2. Same sp2, sp2, sp2. Now, very important, right? So now there's one electron here. Here. Now there are other electron. Now this is the axis. Okay, the perpendicular axis here. Same thing. Same thing. Okay, I'm going to draw it all so that you can have your time. You can fast forward. You like that. Now, give another color for the p orbitals. Okay. Okay, blue, nice color. So this orbital here, the p orbital is unhybridized. So they remain a p shape like that, up here and one down here. Okay, so up here and one down here. Now I'm going to take it. Okay, here got one up here and one down here. So yeah. So it's all like that, okay, up here. Very nice drawing. First try at teaching like that. Okay? So up here. Now, this is the, so there's one electron here, the p electron, okay? Now, how hydrogen here, hydrogen I put a different color. Hydrogen is what? Hydrogen is 1, 1 electron. So it's 1s1. So it's just a s orbital. So hydrogen overlap like that. Okay? Okay. So here the hydrogen here overlap. Okay. So here. Same thing here. Here and here. Okay, and behind here is your hydrogen. Okay. So now remember, that means this overlap here, the CH, I'm going to change the color back again. This overlap is called the CH sigma bond. This is a sigma bond. Sigma. Okay. So there are CH bond. How many CH bond? These are all sigma bond, quite strong bond. Okay, the CH bond is very strong. You can check your data booklet. There is a value about 4 something, 4 or something. Okay, so how many CH bonds are there? How many CH sigma bonds are there? They call CH sigma bonds. 1, 2, 3. There are 6 there. So there are 6. So here I put here 6 CH sigma bonds. Now this the carbon and carbon here. Right? 6, 1, 6, 1 is here 1, 2, 3, 5, and 6. So there are 6 also sigma bonds. Okay, these are all sigma bonds. So 6 sigma bonds for what? Carbon, carbon, single bonds. Okay, talk about single bonds first. Okay, so there are 6 sigma CH3 CH bond, 6 sigma C single bond. Right? Besides that, of course, I'm going to go back to the blue color to show you that. Here is the electron spin down. Okay, spin. Okay, spin. So now, remember these two p orbitals will overlap. Okay, overlap. Top and the bottom overlap. So when p orbitals overlap in this fashion, remember p overlap in this fashion. What kind of bonds are formed? Pi bonds here. If p overlaps in this fashion, if p overlaps like that, what kind of bonds are formed? It's sigma here. Okay, so it's pi. So here, top and bottom, the p overlap. Okay, top and bottom. So here is p. Here is also p overlap. Okay. Here is also p overlap. So top and bottom are p overlap. So how many double bonds are there? How many p overlap? Three double bonds in. One double bond, 2, and then 3. So there are 3 pi overlap. Okay. Right. Now, if you talk about this, that means we will represent this structure. See the double bond here is a pi. It's a sigma. It's a sigma. It's a sigma. Pi. It's a sigma. Sigma is a pi bond here. It's also sigma. It's also sigma bond. Sigma bond. CH sigma bond. Sigma bond. Sigma bond. Sigma bond. And sigma bond. So the bonds are there. So the pi, I've got top and bottom. So it's a flat molecule. And of course, the angle between them is how much? Remember? Okay, the whole thing is 360, isn't it? So it's 120. 120. Right? So this is called the physical shape of the benzene ring. Remember, all this information they ask you from the question. Now, before, after, the final thing is that, see, this overlap is not just here because this carbon is quite near, so this also will overlap. This also will overlap. So that means there is going to be the p orbitals are going to overlap each other, and the electrons here will not only be on this one here, but will be what? Over here as well, over here as well, over here as well, over here as well. Here also. That's why they call they are delocalized. Delocalized. When they delocalize, they become more stable. More stable. For example, here, if you represent your benzene by this molecule, the calculate means a double bond here. Okay. If it's a double bond here, that means that this will react just like an alkane. Alkene. That means it will react with bromine. Bromine will be decolorized. Right? Will be decolorized. Colorized. But it will not be decolorized. Right? Because when you put bromine water into your benzene, the bromine won't react. Why? The double bond is stabilized because of the delocalization of the pi electrons. Okay. So that's why when they all overlap, when the p orbitals overlap, they will delocalize this benzene ring. This is also acceptable answer. I'm going to show you the question. All right. The question is, we talk the first question first. I do the marking scheme. Okay. You're going to do as a question for your homework. Okay, 3, 5, 5. Here. Right. See, describe the structure structure. 3 marks. Describe the structure and bonding in benzene. Whole thing here, I just explain for you here how to get the solid 3 marks. I'll show you here. Sorry, okay. Now there are all the points here. Any 4 3 marks. 4 points. First of all, of course, they say, well, if you see that there's a sigma bond between the carbon, or carbon, which means I told you what, there are 6 sigma bonds between carbon, right? Single bonds, carbon, single bonds, and carbon, single bonds, right? There's 6 of them, 1 mark. And the pi, right? Second one is there are pi bonds formed from overlap of p orbitals. Right now. So there are 3 pi bonds. Right now. And if you mention 3 pi bonds, overlap of p orbitals, you get the mark. Okay. And of course, if you mention that the pi orbitals are above and below the ring, also 1 mark. See? And if you mention that the electrons of the pi bonds are delocalized, also 1 mark. If you mention that the bond angles, the carbon-carbon bond is 120, also 1 mark. Okay. Now, because of the overlapping, the carbon-carbon bond is the same. After I'm going to go back there, picture it's the same strength. Because remember, normally a double bond is stronger than a single bond, right? Because more overlapping, is it not? Right? They found that the carbon-carbon bond, the 6 carbon, the bonds with the carbon, the 6 of them are all same energy. I'll show you after this why. Okay, right? And the same length. They actually took an X-ray photograph of this one. They found that the carbon all same length. How can they become same length unless they have the same type of bonds? This happens because, right, the p orbitals become delocalized. You know, the last point you can mention to get a mark is the carbons undergo sp2 hybridization. Okay? So there are 7 points here. You mention it's 4 points. You get 3 marks. Okay? Let's go look at the other question. Okay. Page 54. Okay. Here getting 2 marks. Too bad. Okay, marking is always different one. Okay. Briefly explain why benzene molecule is planar. Very simple. It's planar because why is sp2 hybridization of the carbon around. Okay. Why is it planar? Because carbons are sp2 hybridization. They form a triangular planar, okay, or bonded at 120, joined by pi. There are 4 variants for you to choose from. The best, of course, is because carbon undergo sp2 hybridization. Right? Okay. Second question here, right? Briefly explain why all the carbon bonds in the benzene are same length. Why? If you go on the Gergely structure, it means double bond, single bond, double bond, single bond, double bond, is it not? Single bond, is it? Now that's called a conjugate system. It means double bond, single bond, double bond, single bond. It's called a conjugate system. Later you learn. Okay? Now why? Of course you should know. Why? Because the pi electrons, right, double bonds are delocalized now. Okay? Pi, you must say the pi electrons or the double bonds are delocalized. Or I can say in resonance, that means they go up and down. Double bonds, single bond, double bonds, up and down. Okay? Or electrons are evenly distributed or spread out. So there are few variants for you to say. The best, of course, is the pi electrons in double bonds are delocalized. That's all they want. Okay, 1 mark is very specific in the answer. Okay? That is for this part here. Okay, so 2 marks here. Okay? Now let's go back to the question, challenging question, which about hydrogen 1355. I want you to go and try to answer this in your house, okay, these 2 questions, right? And answer this question also here. In borazine, B3HN. They tell you that these are the same structures. They have what? Planar cyclic structure. The only way the planar is in the bond between the boron. That means this 3 and 3 is 6 up. So the only way is to compare this to it. You use a brain. Then don't do it. Okay? And they tell you here, the boron and hydrogen atoms are alternate around the ring. Each ring atom has a single hydrogen. It's the same as the benzene. Okay? And they tell you all these things here, the bond length. All boron hydrogen in this one here are 0.144, whereas the simple bonds are Bn, and this one is this one. So there must be delocalization again. So draw the structure. This one. You know, right? So now this is how the question come up in the idea of structure. Why this can be asked? Because the sp hybridization is found in the physical chemistry. Even though here you can see that it is not in here, they can still ask you. Now we go to they ask you for reactions. The key word is reactions. There's my pen here. Okay. Reactions. Right? So the first one we talk about is the structure. Now, what kind of reactions are there? You got 1, 2, 3, 4, 5. 5 types of reaction. Never mind. Just let me explain to you first. The key word, they will ask you for the mechanism. Now, the key word is here. Okay? Describe the mechanism. And the name of the mechanism is called electrophilic substitution. I'll explain this, what it means. Okay? I'll give you, first of all, the whole viewpoint first. The whole, I call this spider diagram or whatever you call this method. Okay? Right? Now, they say here is substitution. Okay? Here, substitution. First is chlorine and bromine. Okay? This measurement. There is nitration. Okay? That means chlorine, bromine, means you're going to put chlorine there inside here, you're going to put bromine inside there to kick out the hydrogen. You're going to put hydrogen, means NO2 inside there. Hydrocarbons alkylation. Alkylation means they're going to put a CH3 inside there. Acylation is a new word to use. Acyl means you put that. Okay, C number one O and CH3. It's called acyl group. Okay. These three are substitution reaction. Something goes in, something comes out. I want to kick out the hydrogen here and put in a bromine here. It's called substitution. Okay, I want to kick out the hydrogen here and put in a bromine here. I want to kick out the hydrogen here. Okay. I want to kick out the hydrogen here and put inside a CH3 group here. Kick out the hydrogen here and put inside here an acyl group. C double bond O and CH3. And all these are called what? Substitution, and they are called electrophilic. Okay, now the word substitution means something, a group comes out and another group takes over. Electrophilic means these fellas here, all these fellas here, I'm going to look for love electron. Philic means love electrons. Okay? Philic means file. Okay, electrophile. That means love electrons. See? Right. So they're going to kick it out now. We're going to look at the whole picture first. I'm going to draw for you. Place here. Right here. Now, I'm going to put benzene here. C6H6. This is my first reaction here is with Cl2 or Br2. You understand? They cannot react by themselves. In the cold, in the dark, cannot react. Of course, if the double bond here is like your alkenes, you can say. So they need something to help them, a catalyst. They call it a halogenating agent. In this case here, you can use Fe, Cl3, or Fe, Br3, or iron with chlorine and bromine here, and you heat. Okay? So if it's chlorine here, you will get chlorobenzene. Okay? Means you're going to kick out the hydrogen there, which will form the ring here, and plus your HCl. If it's bromine, you get the bromine, the bromine here, and of course your ring, okay? Plus HBr. We'll look at the mechanism later. So this is the first one. Remember, these are all undergoing electrophilic substitution. Now the second reaction, of course, here is a nitration. Okay, we call it nitration. Or in this case, it's called chlorination. Or they call it bromination. Or the general way is called halogenation. Nitration. So what do you do? How do you make this into something that will attack here? Remember, the ring here is the benzene ring is rich in electrons. Remember, we have got the I'm going to change the color. We have the we call it the delocalized pi just on top. Okay, so that is our electron. This is called the electron pi. Is rich in electrons. So what we attack here, of course, will be positive X here, because it's charged positive. So positive, it means that they like electrons. That's what they call electrophiles. They're called electrophiles. Phile means like that. Okay, so like if you like sound system, got audiophile. If you like, the sex word, like pedophiles, I'm sure you know the word. Okay. So now all these here, the chlorine must become Cl minus, Cl plus. Bromine must become Br plus. Okay, that's our new deal. Nitrogen must become NO2 plus. Sorry, yes, 2. 2 plus. Okay. So now what do we use to nitrate? We use a combination of 3 things here. First of all, concentrated must be concentrated HNO3. Okay, nitric acid, concentrated sulfuric acid. And the temperature, normally in most examination, they put 55 degrees centigrade. Very low. Okay, I mean, your Bunsen burner can give about 200, 300 degrees centigrade. So it's very low. Less than 100, you just boil a bit, heat a bit, you can get rid. Okay, of course, here you get your nitro benzene. And from here you can get your TNT now, nitrotoluene. Okay, now you put this one here. Okay. Now this is called nitrobenzene. So these are the 2 substitution. Now the third one, of course, I'm going to change my color. Right here. Of course, alkylation. They call it Friedel Crafts. Okay, don't forget about that one. Okay, it's called alkylation. I want to introduce an alkyl group there, a CH3. So which means I want to produce like something like CH3. This substance. What is this called? Methyl benzene. C6H5 CH3. So now what do we use to substitute the hydrogen for CH3? Very simple. You normally, if it's CH3, you put CH3 here and you use an alkyl halide Cl. I want to carry the chlorine away, so I use the same thing as F. Can use FeCl3, but normally they use aluminium trichloride, AlCl3. And this heat. You can also use AlBr3. Also can use FeCl3 also can. All this will carry away the chlorine and put this as CH3 positive. So the CH3 must be CH3 positive. Lastly, of course, in this, I go to the other one, in electrophilic substitution is, of course, acylation. Acylation. I want to introduce the CO double bond H1. Okay. So we use this further here. Okay, C double bond O. This one there. Okay, and the chlorine here. The chlorine must come out. So again, I have to carry it out. I use FeCl3 or AlCl3. It's very active. So this whole thing will come out, and you will get what? You get what you call a ketone. Don't worry about it. Okay, double bond here, and the CH3 here, and here. See now. Okay. Okay, don't worry about the name first. Now, okay, all these are called what kind of reactions? What kind of mechanism? What kind of chemical reaction required? Now, the name for it is called electrophilic substitution. Electrophilic substitution. It's a name and also the mechanism. You can see how this is called. It's the name of the reaction. Name of the reaction. Okay, and the name of the mechanism. Same. You will see after our tissue. Okay, electrophilic substitution. Of course, fine. Now here you look at it. Here they ask you for one more reaction here. Right? For benzene, we have this thing called here, hydrogenation of benzene ring. We want to talk about oxidation first. Okay, here the last one here, which is here, hydrogenation of benzene ring to form cyclohexane ring. Okay, the last one we're going to complete here. Right? So I'm going to put hydrogen inside here. All right. Now remember all this. This one here, all these are called substitution. Now here is addition, hydrogenation. Hydrogenation is under addition reaction. That means something goes in, nothing comes out. Plus hydrogen. Normally you use nickel, you must heat and heat. You must heat one. Okay, if you use platinum, you heat better lah. Platinum. Of course, you get all the double bonds with hydrogen. So it's C6H12, which is your cyclohexane. Okay, it looks like this. Okay. Okay, cyclohexane you should beat in your hydrogen here. All of them become sp3 already. Hybridization now. Okay, I will just put H2 here. Okay, H2 here, H here, no space. This is called your cyclohexane. So one addition reaction, I'm going to put a different color so they can see. Okay, yellow. So this addition. Right? All this here are what? Reaction? Substitution. So you can see this is the big picture, okay, which we're going to look in later on each of them here when we do our mechanism. So you can read Bye, and thank you for watching. A few questions. I want you to go to homework. The homework is, remember the 2 pages here? Page 355. Do it to see your